Hello everyone, my name is Balma and I'm a mechanical engineering student at Izmir Institute of Technology. In this video, we will examine sheet metal forming processes based on Chapter 16 of Manufacturing, Engineering and Technology textbook. Sheet metal parts are used in many areas such as aircraft bodies, automobiles, and kitchen appliances. These parts are important because they have a high strength to weight ratio and are generally easy to manufacture in large quantities. Let's start with shearing. The manufacturing process usually begins with shearing. In this process, a punch and die are used to cut the metal. If you look at the sheared edge, we can see four main regions: the rollover, the smooth burnish zone, the rough fracture zone, and finally the burr at the bottom. To get a high quality cut, the clearance, which is the gap between the punch and die, must be calculated correctly. To find required force for this operation, we use the formula right here, where T is thickness, L is the total length of the cut, and S is the ultimate tensile strength. Let's continue with material characteristics. Not every metal behaves the same way during forming. A metal's elongation ability determines how much it can stretch before it fails. Another important factor is anisotropy, which means the metal has different properties depending on the rolling direction. If the material or the process is not correct, we might see defects like leader's bends, which are visible stretch marks on the surface, or an orange peel texture, which is caused by a large grain size in the metal. Now let's look at bending. When a sheet is bent, the outer part of the bend is under tension while the inner part is under compression. Between them is the neutral axis where the length of the metal doesn't change. So we can calculate bend elements by using these formulas with an bending angle, bend radius, and thickness. Now let's continue with minimum bend radius. It is the smallest radius we can bend a sheet without cracking the outer surface. This happens because the outer fibers are under high tension. We calculate it using with these formulas. Here T is thickness. We will use T from the table above in accordance with which material we will use. And R is the material's ductility. So the more ductile the material, the sharper we can bend it. And also, as you can see from the image, always bend across the rolling direction. If you bend parallel to the grain, the material is much more likely to crack. In short, stay above the minimum radius to keep your part strong and crack-free. The biggest technical challenge in bending is spring back. Because metals have elasticity, the part will slightly open up after the load is removed. Engineers compensate for this by using overbending, which means bending the part to a smaller angle than required so that it reaches the correct angle after it springs back. We can also calculate the bending force. We calculate this force to select the right machine, like a press brake, for the job. The maximum bending force is calculating by using these formulas. And K is a constant based on the die shape. S is the yield strength. L and T are the length and thickness of the sheet. And we also use the die opening width. And to calculate spring back, B, we use initial radius and final radius. To summarize, successful sheet metal manufacturing requires accurate calculations of cutting forces, material properties, and springback levels. Understanding these parameters during the design phase helps minimize production errors. Thank you for listening. And in the next video, we will perform an ANSYS simulation of these processes.